Hi, my name is Neil Butterworth, and I'm going to take you through a presentation on the value of fire engineering for architects and engineers. When John asked me to do this presentation, he gave me a title of Getting Value from Fire Engineering for Architects and Engineers. So I've sort of thought that is the what, when, why, and who of fire engineering. Which is what I'm going to talk about. But in chatting with John, he also said, could I put in a few project examples? That's the sort of thing that people like to talk about, like to see. And if I could sort of give 4 or 5 key messages of what I'd like people to take away from the presentation. One of the things to say in terms of what I want to talk about, the what, when, why, and who of fire engineering, is it's a kind of a non-linear thing, but because time works in succession, I need to talk about them in some sort of order. But they're obviously all interconnected. You know, who you need to do the fire engineering depends on what it is you're trying to do, when you do it, etc. So just bear in mind there's a little bit of interconnection going on here, but I've got to try and present it in a chronological fashion. So I thought I'd start with what is fire engineering. And I looked up some dictionary definitions of engineering, and it's kind of like about the application of science. Basically, the same can be said of fire engineering. It's about taking fire science, fire principles, and applying them in real-world situations. But what we often have at the moment in the world of fire engineering is the sort of concept that there are 2 approaches that you can use: a prescriptive approach or a fire engineered approach. You can just follow the guidance, or you can actually start trying to apply some science. And those 2 distinctions allow some comparisons to be made. And the sorts of comparisons that I often hear being made, prescription is simple, it's conservative, in other words, it's safe, it's quick, it's low risk in terms of obtaining approvals, and prescriptive buildings are easier to manage because they don't contain all these complicated fire-engineered systems in them. And then the converse being true of fire-engineered buildings. They're complex, they're trying to reduce safety because that's what we do as fire engineers, isn't it? There's an inherent design and approvals risk, and they require special management. I got some images from the London Fire Brigade. These are courtesy of the London Fire Brigade, of what can happen when fire design goes wrong. These are just some images of fire-damaged buildings. What I found interesting about these images is none of these are what you would call fire-engineered buildings. These are all buildings that followed prescriptive guidance. And yet, following that prescriptive guidance can still lead to situations where serious damage and risk can occur. And of these fires, when you look at them, most of them were avoidable through simple good design practice. It didn't necessarily have to cost any more. It just needed people to make the right decisions at the right time and put the right systems into the building. So they weren't fire engineered, but in my view, they should have been well designed, and we should have been applying the right thought process and the right design process in the development of the fire strategy. So the first message I'd like people to take away from today is adopting prescription doesn't negate the need for good design. You still have to think about what you're doing. And the prescriptive guides are there for the more common types of building. You need to determine whether your building is a common type of building, whether that includes typical demographic of people, whether there are the normal sort of fire hazards, whether it's being built out of what would be considered common construction methods. And you still have to apply that thought process rather than just simply reading things from a book. And I've got some examples here where Arup have done things differently from the prescription, but because we felt the prescription wasn't meeting the needs of the building or the client. First one here is the Leeds Arena. There are 2 things about this building. The prescriptive guidance would say that the roof structure could be unprotected. It was really there only to support the roof, but in our view, this building is almost essentially a roof. It's a big, large roof over a large number of people, and that actually losing that roof is not really an acceptable outcome from a fire event. So we actually decided that it's not acceptable just to assume that that roof can be unprotected, and we looked at all the different types of fires that you might have in that building and worked out which elements need to be protected. There are still a lot of unprotected elements in there, but those that could be exposed to a severe fire are actually protected to prevent damage occurring. Similarly, in the facade, we designed the building, got to a certain point, it got handed over to a contractor. Inevitably, you go through a value engineering process, and the contractor proposed a different insulation material for the facade. Now, the insulation material, there's a lot of it, because it's acoustic insulation more than anything, actually. And it's in a congested city centre site where a lot of insulation material was required. And this particular material that was being proposed by the contractor would have been acceptable to the local authority, building control, and it would probably have complied with the requirements of the building regulations. However, our view was if you got a fire in that facade for whatever reason, the spread of fire would be so rapid through the building, reputational damage, all of those sorts of things that need to be considered would just be unacceptable. And we had to work quite hard with the contractor to convince them actually they shouldn't be using this material. In the end, they saw where we were coming from and decided it was also in their best interest not to use the material that was being proposed. Just a picture of it in construction there. Here's another very simple example. In this particular building, the fire strategy, for whatever reason, the fire strategy was trying to divide the building into two compartments, Zone 1 and Zone 2. And the fire strategy relies on fire spread not occurring between Zone 1 and Zone 2. So if you look at prescriptive guidance, we put the compartment walls where the solid red lines are shown. You take them up to the edge of the building, and that's fine. You don't need to think about it anymore. So we could move on. However, what about a fire that's located in that room and it's spreading actually across the courtyard through radiation? The code doesn't necessarily require you to use that, but to consider that, but the science and the physics is that it can happen. So you need to be aware of that, and if your strategy relies on it not happening, you need to prevent it from happening. Okay, so when to use fire engineering? So we've seen some of these iconic buildings, large tall buildings, Olympic event buildings, some of the more complex buildings where I think are often associated with fire engineering. However, my experience is that actually many of the smaller buildings offer equally and interesting challenges. But actually, more importantly, is if we ask the question, rather than when should we use fire engineering, we ask the question, when should we use good design? Surely that's in all buildings. And so really what I'm advocating is, it doesn't matter the scale of the building, the expertise that get applied and the thinking and the design process must be commensurate with that building. And so fire engineering applies to some extent in all buildings. What about in the timeline of a building? Often, or in my experience, fire engineering and fire strategy writing and development happens in the design stage. And actually, I pulled out some typical scopes of services for fire engineers, and we even tell people that this is where fire engineering is done. And quite often we go through a scope and we get to the end of something like stage E, where the detailed design is done and it's handed to a design and build contractor, and the fire engineering scope sort of becomes, ad hoc advice. But when you actually think about the problem in hand, what we need to do is we need to have a successful outcome. We've got to think about the preparation, engage with clients and stakeholders. What do they want out of the building? How do they want to use it? How are they going to operate it? How are they going to run it? What fire safety management procedures are they going to have in place? Therefore, how must we design it to meet that needs? Once we've designed it, how must we specify it to make sure that actually what was designed was built? We must check that what was specified is actually built. And then we have to monitor and maintain and run it and operate it in accordance with the way that we said we were going to, and the manner in which the design is based upon. So again, it's a non-linear process, really. We've got to think of it all the way around, and that the fire strategy is integral in all of those stages. So once again, we have to apply the right skills at the right time throughout the process, not just in the design stage. And again, some examples here where just to make that point. So often the code or prescriptive requirements would be for mobility impaired escape wheelchair users, you provide a wheelchair refuge in the stair, and there'll be assisted evacuation by the operators of that building who might do a carry-down facility to take those people out of the building. But this begs two questions. How do we know one wheelchair space is actually enough? How many people are there likely to be on that floor using wheelchairs? And have we incorporated enough space for those people? And we're finding more and more and more clients don't want to, or actually refuse to, ask other members of their staff to effect a carry-down, in which case that strategy doesn't work. And we have to know what our clients want to do and how they're going to run the building so that we can design it correctly in the first place. Here's an example about specification. One of the things that we do in fire engineering where we're doing calculation is we'll calculate the amount of vent area required to allow smoke to vent out of the building. And we'll come up with a free area, or we'll come up with a vent area. And we have to be very careful what we mean by that vent area, because if we actually ask for 30 meters squared of vent, the vent manufacturer might say, well, yeah, those windows, when you add up the area of the windows, add up to 30 meters squared, therefore 30 meters squared of vent. But what we actually mean that we need is the free area of vent through which smoke can flow out of. So if those vents only open 30 degrees, I don't know what the equation is, but they're only about a third of the free area of what the actual opening area is. And I've seen this time and time again where there isn't enough vent provided because of an imprecise specification of what we actually want. Another example about the disconnects that can occur. This particular building, these lines here where you can see the sort of red dashes are compartment lines required for compartmentation in the building. But the red lines indicate where there's glazing. So that was specified as being, I don't know what it was, 60-minute glazing. And sure enough, the glass was bought from somebody, and they asked for 60-minute glass, and they've got 60-minute glass. And then the window installer got the glass and has installed it in their window frame. Now, the window frame that's been used in this particular instance is a softwood window frame that gives you no fire resistance at all. So you've got this beautiful 60-minute glass in a 60-minute wall with a frame that's going to fall out at the early stages of the fire, and you've got a gaping hole in your compartmentation. And in this particular instance, they've had to take out all of their frames and reframe it in a hardwood frame that gives you the required fire resistance. So again, it's this thinking the process right through. It's about ensuring that you're specifying correctly and that what's being put in is actually correct. Some more examples. Fire stopping, one that we see all too often, fire stopping installed incorrectly. And actually what I find quite interesting with this, particularly some of these later pictures, and I'm no expert here, so I couldn't tell you exactly what's right and wrong about these installations. But to a layperson, they certainly the two on the right look about right to me, but they're not. And so it's important that, again, that the right competency is applied through the process so that you know that fire stopping is being put in correctly. And what's the point of going through all this design process of specifying and thinking about the fire strategy when it's not being built correctly? So, message 2, total fire engineering, a concept that we're using, a terminology we're using at Arup, means a good design, construction and operation. We've got to go right the way through the process and get it all correct for the whole thing to stack up. Okay, so why use fire engineering? Well, really, fire engineering services need to enable our clients to achieve their aspirations and their requirements. So it goes back to the slide about engaging with them in the preparation, finding out what they want to get out of the building and allowing that to happen. And And we need to give consideration to the design and construction phases, and we need to add value to our projects. But that value can manifest itself in a number of ways. I've listed, a few here, but there's a whole bunch of things. But the important thing is it's not just about cost savings. There's legislative compliance, protecting clients in that respect, making sure they are complying with the legislation, reducing risks within buildings. We can improve quality and function of space. We can improve commercial viability of the building, and I've talked a fair bit about the quality of construction, ensuring for clients that they're actually getting what they've paid for. And again, just going through a few examples, Heron Tower was characterised by what they called a village concept, where there were villages that comprised 3 floors that were interconnected, and the idea was to let to tenants who would actually like to take up 3 floors and have connectivity between those floors. So there were sort of little mini atria connecting the 3 stories. And it occurred to us in this instance that a 3-story fire was a real possibility that needed to be considered. And so we actually did the full analysis of a fire on 3 floors to see how the structure behaves and show that it could survive the fires that we expected it might be exposed to. So that's an example where we went, quite a bit further than what the code would expect you to do, which is just apply 2 hours fire protection and kind of forget about it. Here's an example just showing at the other end of the extreme from structural fire engineering. This is a smallish school where we were involved at the other end of the scale, did some simple hand calculations on composite steel frame beams using methods not dissimilar to the SCI method that Ian presented, and we were able to make some cost savings by omitting fire protection from selected steel members. This particular example actually is it's a fantastic building built into the hillside, but it's a relatively simple building, a visitor centre, but the previous one had burnt down, so this client was pretty nervous about getting it right. And actually much of what we did was just client management, and they saw the value in us doing precedent studies, looking at how these things are done internationally, just to give them confidence that what they were doing was actually the right thing. This particular example is about a series of projects that we've done with a client in Manchester. And on some of the earlier projects, that client is a developer client. They were very interested in the capital cost of the building, and they really wanted us to reduce that as much as we could. We kind of said, "Are you sure about this?" And they said yes. So we went along with that approach. And one of the things that we managed to be able to do was eliminate some of the lifts from the building. And subsequently, having built it, what the client found was that building was less easy to let, because the lifts that we eliminated were lifts that could have been used to evacuate wheelchair users, but now the clients, the potential tenants, were being asked to effect a carry down, which they didn't want to do. So our client actually saw this as narrowing their market of lettability. Yes, they've got a cheaper building, but it's less easy to rent to the market. So now when they come to us for fire engineering, right at the top of the list of what they want us to do, of our goals and objectives, is to improve their marketability and their lettability of the building, which often means putting in more things than what you actually have to comply with the legislation. So, third message, it's not all about cost saving. We're getting there. This is just a little bit of a tangent. When you often fire engineering, we think about it as being life safety, and the goal and the objective that we're trying to achieve is the minimum standard required for life safety. Sometimes people go further than that, and they'll ask for a particular quality of space or functionality of space, and sometimes they'll ask for the reduced capital cost or reduced operational cost of the building. But our view at Arup is that actually we need to start thinking and really engaging in the sustainability debate. And the way to do that is to express your goals in terms of social, economic and environmental goals. And what we need to really start thinking about is the total cost of fire to the life cycle of the building, where the total cost is the cost of prevention, cost of protection and cost of occurrence. So we're balancing the amount of protective measures that we put into a building versus the change in damage that would result as a fire with those protection measures. And it's only once we've got that balance right and minimizing the total cost that we can be sure we're getting the most sustainable solution. And when I say cost here, I'm using that term, but it doesn't have to be financial cost. It can be social, economic, or environmental cost. It's a really easy equation to write down, really difficult equation to solve. We've got some work to do to be able to answer all of those questions, I believe. But I do believe that's where we've got to go. Otherwise, the sustainability debate's going to pass fire engineering, and we need to engage in that. So message 4, we have to start addressing the total cost of fire on sustainability. Okay, so getting into the final bit, who to use for fire engineering. Well, when I thought about this, a colleague of mine had attended a Royal Academy lecture a year or so ago for engineers, and they were talking about engineering ethics in practice, and they came up with these 4 main pillars of ethics in engineering. And one of the top ones was accuracy and rigor. And within that, there was effectively, I think this has been paraphrased, but it's effectively a statement of it's not ethical to work beyond your competency. And so I got thinking about that in terms of fire engineering, and going back to the beginning of the presentation with this sense of prescriptive or engineered, or following code or applying science. I think the important point is it doesn't matter which one of those you use. There's value in informing the design process as to whether you use prescriptive guidance or whether you use engineering science. But the most important thing is to be using the right competency for the problem in hand, and using the right competency all the way through the process. It's not just about the design, as I've shown. It's the right competency during specification, during construction, and during the use of the building. And I also looked at some papers from Margaret Law, and she wrote about competencies and talked about what are the competencies required for fire engineers. And we've got education, training, knowledge, awareness, experience, research and development, and intellectual toughness was a term that she used. And she asked the question back in 1990, what makes this list different from any other aspects of engineering? We expect our structural engineers to design buildings in that manner. We must expect the same of our fire engineers. And her conclusion at the time was that there is no difference, but only that with fire safety engineering, we've got to keep spelling it out. And it still feels a little bit like that. We've still got to keep spelling it out, that actually this whole thing of just simply having a prescriptive code that people can follow is not a panacea. We have to have the right competencies behind that. So, message 5, competency, competency, competency. And so that's about it. So just some closing remarks just to summarize. So the what, when, why, and who. Well, hopefully I've made it clear that I think fire engineering is actually not necessarily just the application of science, but it's the expertise that are required regardless of the situation. When, it can be simple or complex buildings, but importantly it needs to be from inception through to operation. Why? There's quality of design, innovation of design, efficiency of design, as well as, in many cases, cost savings. Who, I'm not going to stand here and say you should be appointing Arup on every single project. That's just not the case. But what is important is you have the appropriate competency for the building and the stage of the involvement. And those who are responsible are obliged to assess, for selecting the competency, are obliged to assess that competency and make sure that the right level is being applied. Sorry, I'm repeating a little bit here. Fire engineering is not always required. And my messages, following prescription does not negate the obligation for good design. Fire engineering is about the whole process. Value goes beyond cost saving. We have to start assessing the impact of fire on sustainability, and the appropriate competency must be provided throughout. And I find myself finishing with this slide quite often in presentations I give. Ove Arup was quoted as saying, a long time ago that great things can happen when all relevant design decisions have been considered together and have been integrated into a whole by a well-organised team. And I think inserting the word fire on the first line there, you couldn't say it better, in my view, from fire engineering. That sums it up. That's what I think is required and what makes a good fire engineering design. So thank you very much for your time.